Alrighty, we shall continue with our discussion of chemistry. So we've already started some on chemistry. We talked a little about the periodic table. We're going to talk a lot more about the periodic table today. So the elements. Now remember, what is an element? Well, an atom qualifies as an element, so I'm going to take that as a yes. But the book makes a statement about elements as being all of the atoms are the same type. So one atom is always going to be an element because it's always its own type. But if you have something like elemental iron, that means that all of the atoms are iron. And of course, it's never 100%. No, it's never 100%, but 99 point whatever percent. So element is all the atoms are the same type of atom. And there are 115 different kinds of atom according to what I have here. Now, it's been a couple years since I have gone through and counted anything. A couple years, actually, just 1 year. But if you look at our periodic table here, you'll see some interesting things. You'll see, these ones here that are white, those are white, I think because they don't naturally occur, you don't find them in nature. They're only made in laboratories. These here, UUT, UUP, UUS, UUO. As of about a year and a half ago, those have changed to standard names. They're like nihonium is one of them, and I think moscovium is one of them. I don't remember what the others are, but these now have been named. And so you might wonder, why did they have UUT? UUT was what? I couldn't put church name. Anyway, it's just 113 in using a number code. UUP was pentium, right? 115. And septium and octium. So whatever. They were placeholder names. But now that they have been discovered, that is, they have been created in the lab with enough certainty that they actually created them, they have been given names based on the people who found them. So if you look at the names of the elements, now, of course, when you look at those, you don't see names. You see BE, right? You don't see beryllium. You don't see boron. But all of those symbols are standing for names. And when you get down to the lower ones, the names become more interesting, at least to me. You have things like, CA. What do you suppose CA stands for?
Oh, we know.
It's California, for California, because it was discovered at the University of California. And then there's B, I think it's BK. BK, yeah, right next to C. Okay, it's CF actually for California, not CA, CF. CA is calcium, what was I thinking?
Yeah.
Calcium up here.
I know.
Yeah, CF for California. But you have here, just before California is BK, that's berkelium, because it was found at Berkeley Lab, University of California. AM. Americium. Americium is actually something we use a lot. Smoke detectors use americium in them. And so that's named for America. NP and PU. NP is neptunium, PU is plutonium. Notice those are right here next to U, which you probably know. U is uranium. NP was the first man-made element. The first element that was synthesized on Earth that didn't exist on Earth. And so we have Uranus, which is a planet, and based on variations, actually, a little history of astronomy, just because it's kind of in this class anyway. Planets were, the name planet means wanderer. Don't put this for your potential test question, okay? The astronomy stuff is not the topic du jour. But the planet means wanderer in Greek, and they were the objects in the sky that didn't move with the rest of the stars. And so back in the day, even the moon would have been a planet because it was something that moved with respect to the other stars. Well, in observing these planets, Uranus was discovered. It's actually discovered a couple times. You know, first person discovered, didn't know what they had found. And so William Herschel is the one that gets the credit for discovering it, he and his sister Caroline. And they actually tried to name King George's star. Well, it was Georgius Siderius, I think was the Latin name. But that wasn't an allowed name, so it's named Uranus after a god. And then based on wiggles in its orbit, it was predicted there must be another planet beyond Uranus that's causing Uranus's orbit to wiggle and not do the shape we think it should do. And so scientists aimed their telescopes at the predicted location, and they found Neptune. And then looking at the orbit of Neptune, they said there must be something additional that's causing wiggles in Neptune's orbit. And so they looked where they predicted, and they found another object, and that was Pluto. Now, it turns out Pluto, they very quickly realized, was not the right object. It didn't have the mass necessary, blah, blah, blah. Pluto is no longer considered a planet because it doesn't fit in with the rest of the planets. But Neptune and Pluto were the first two predicted and then found planets. We look at the periodic table, we have the same relationship. Neptunium and plutonium are the first two man-made elements that you get by bombarding uranium. So you have the same sequence: Uranus, uranium, Neptune, neptunium, Pluto, plutonium. Then we have americium, curium, named after Marie Curie, berkelium, californium, that's Einsteinium, obviously that's named for it. Fermium for Enrico Fermi, Mendelevian. This is Mendeleev. It's called the Mendeleevian periodic table. Mendeleev is the person who came up with this organization, so that's why it was named after him. Nobelium for Alfred Nobel. What's Alfred Nobel? Where did he get his money? Do you know? From what? From finding a way to stabilize trinitroglycerin to make dynamite. That's how he got his money. So when they talk about the Nobel Prizes, they're giving out, $2 million roughly for a Nobel Prize. That's why it came from the development of dynamite. Is dynamite a good thing or a bad thing? It can be both. I think of it as a good thing because it allows us to do things like clear out areas and make roads. Lots of good things with dynamite, but there's also some negatives. Although these days, if you're actually making a bomb, you don't make it out of dynamite. You make it out of, something else. L.R. Lorenzi. The names, I think, are kind of interesting because they have a lot of history in the man-made elements. So 115 of these distinct different types of atoms, only 90 of them are found in nature. So if you count the ones that are dark, you should only get to 90 counting the ones that are dark. The other 25 have to be synthesized. Now, this is kind of interesting because we talked about atoms and we said that the atoms, they're eternal. They're eternal unless you do something to them. Do something like bombard them with very energetic objects. So there are ways of changing the atoms, but it's not just through chemistry. It's through particle accelerators, making them bang into each other. And so an element is a material that consists of only one type of atom. Here was our definition repeated. We talked about the protons and neutrons. An important thing is to know that protons and neutrons have about the same mass, and electrons are about 1/1800th of the mass of a proton and neutron. So if we look at the masses, if we take a bowling ball as a proton, then an electron is about 1/2000th of a bowling ball. A bowling ball is what, about 10 pounds roughly? So 10 pounds divided by, let's just make it 2,000 to make life easy. That would be what would that be? 10 divided by 2,000 would be 5/1,000ths of a pound. Right, so the electron is really minor compared to the things in the nucleus. So when we talk about the mass of an atom, we can ignore the electrons. You have a lot of electrons, it's just not significant compared to one proton or neutron. And if it's neutral, as we talked about, you have the same number of protons as you have electrons. So electrons, all electrons are identical. You can't distinguish one electron from another, which leads to a lot of interesting things in quantum mechanics, which is not part of this class. Remember, we learned that opposites attract and likes repel. So electrons are attracted to protons, but repelled from each other. Proton. I've already talked about a lot of these things. Nucleons is a term for things that are in the nucleus. So the nucleons are only two types of particles, protons and neutrons. That's all you have in the nucleus. And we've already talked about the words isotopes and isotones. And so let's talk about the atomic mass. The atomic mass is a name that means the total mass of the atom. And so the atomic mass, the total mass, is the number that's written in the bottom center of those squares in the periodic table. And because protons and neutrons have almost exactly the same mass, we can just count the number of protons and neutrons, and that gives us a rough number for the atomic mass. So we just add them up, and we say each proton and neutron has a mass of 1 atomic mass unit. So the atomic mass unit is a nice, easy way to allow us to just say we're counting protons and neutrons. And so that atomic mass unit converted into standard units is, one atomic mass unit is 1.661 times 10 to the minus 27 kilograms. Now, well, I will leave it at that for now and not mention the next piece of that. When you look at the masses back there, they're not integer numbers. They're not integer numbers for a couple of reasons. Reason number one is that is taking the average for a sample of elemental material. What does it mean if it's elemental?
Only one atom?
It has only one type of atom. So, like I've been using the example of elemental iron. All of the atoms in this chunk are going to be iron if it's elemental iron. Elemental gold, they're all gold. With metals, we also can talk about alloys, which are mixtures of different metals. So when we look at an element, and so since I'm talking about iron elemental, we can look at iron here, and we see that it has an atomic mass of 55.845 units of atomic mass units. If you take this number, multiply it by that 1.661 times 10 to the minus 27 kilograms, that tells you the mass of one atom of iron in kilograms. But this isn't an integer. It's not an integer because it's the average, and you have more than one isotope of iron. You have more than one number of neutrons that you can put with the 26 protons in iron. And since there's more than one stable isotope, you're basically taking an average. This one is 30%, this one's 70%. I'm making up those numbers. And so the total mass is that combination. So that's one reason why it's not an integer. Another reason is, and this one's kind of funny, while the mass of a proton, the mass of the neutron is set, those are the values if they're by themselves. If you bring them together, the mass is lower than the mass if you have them separate. That's like saying if I have two magnets and I let the magnets come together, the mass when they're together is lower than the mass when they're apart. Does that make sense? People are nodding their head. To me, it doesn't make sense. To me, the mass should be the same. I got this magnet, I got this magnet, I add them up, that should be the total mass. It shouldn't matter if they're far apart or if they're together, it should have the same total mass. But it turns out that in nature, one rule that we used to think was true that we found is not, is the rule of conservation of mass. Have you heard of conservation of mass? It's not true. Mass is not conserved. You can change mass. You can convert between mass and energy. And so, just as with the magnets, they go to a lower energy when they come together. That's why they come together, because it's lower energy. But when they go to lower energy, they release some of their mass. And so they have less mass when they're together than when they're apart. With the magnets, the difference is so small we would never be able to measure it. But with the atoms, the difference is much bigger. The energy to hold the nucleus together is very strong. And so the mass changes by a measurable amount. That's really important. You guys have heard of atomic bombs? That's where the energy comes from. An atomic bomb makes the energy by changing the nucleus so that you're going to a lower energy state in the nucleus, a more stable nucleus. It's kind of like taking this, and I have this up here. It's at an elevated gravitational energy. I let it go and it goes down to a lower gravitational energy. Now, there was nothing exciting with that because they're so light that air made a difference. But this, if I drop it when it hits the ground, what's it going to do? When it hits the table, it'll bounce and it'll make a sound. That's what's going on with the bomb. The nucleus is going to a lower energy state and releasing energy. In this case, you heard a sound. In that case, it's so much more energy. It's a big shock wave, very high temperature that is released because it's gone to lower energy state. And so you can convert mass. That's another reason that those masses are not just the simple integers. Okay, our first of the clicker questions for the day. The atomic number of an element matches the number of what? Who? Did I say the atomic number? Not today, I don't think. I think I did Friday. So let's see what we know. And I am guessing that most of you will be wrong because, we didn't talk about this since Friday. Okay, everybody's in. I totally can't read one of the numbers because it's the same color, but 3, 2, 1, that makes 6. It must be 2. 3, 2, 2, 1. I think that's what people, no, that would be wrong. 3, 2, 1, 1. Okay, so we did not have a majority. Leslie, what do you think the answer is?
I think that it would be for sure the protons in the nucleus of the atom. And the fact that it says electrons in a neutral atom means that there's no change in the electrons. So then the protons and the electrons would be the same.
Okay, she nailed it. Both of these numbers turn out to be the same. Technically, this is the correct answer. But because the two numbers are the same, I wouldn't put this on a test because both of those would be correct. Unless I said, which one is the technically correct one? Which is kind of a harsh question because you're like, but if you know that the two have to be the same, you're like, well, which one is it? Is it the number of electrons or the number of protons if they have to be the same? So it's the number of protons in the nucleus. Electrons in a neutral atom is the same as the number of protons in the nucleus. So C, both of the above, would have also been a correct answer. So the only one that would work would be none of the above. Now, let's talk about other words here. So the atomic number is the number of protons in the nucleus. We just talked about the atomic mass. What's the atomic mass? Total mass of atom, singular. So of all the protons and the neutrons, it's also equal to the number of protons plus the number of neutrons. Because a proton is one atomic mass unit, the neutron is one atomic mass unit. The total atomic mass is just 1 times the number of protons plus 1 times the number of neutrons. So those are both correct, the total mass or the number of protons plus the number of neutrons, because the atomic mass unit is just the mass of a proton or neutron. There are 2 other numbers. This n here was the neutron number, very clearly the number of neutrons. And then there's the electron number, the number of electrons. Don't really need to define those because the name says it all. Okay, about the periodic table. Things you don't need to do. You don't need to memorize it. Right? If we were taking an intro to chemistry class, yes, you would have to memorize the elements and at least some of them and so on. You don't have to for this class. On the test, you'll have a periodic table, something like that. Obviously not on the test this Friday because this material is not on the test this Friday. But you'll have the periodic table that you'll be able to use. It will have the symbols for the elements. It won't have the names of them, but except for some very obvious ones like oxygen or carbon or hydrogen, I'm not likely to expect you to know what a symbol means. But you do need to understand that the periodic table is an organizational table for all of the elements, for all of the different types of atoms we can have. And learn how to read it, learn what it means by the position in the periodic table. So what do we have there in the periodic table? We have different columns for similar chemical behavior. The lower it is, the higher the mass. The different columns we'll talk about in just a moment. Oh, here I put the names of the new elements. So 113, the one that is listed up there is UUT, tritium, is now known as nihonium. Yeah. Anyone here speak Japanese? Nihongo hanashimasu ka? Skosh. So Nihon is how the Japanese people say Japan. So Nihonium is Japanese. Muscovium. What's that? Moscow, yeah. And Tennessee, yes. And Oganison, I think, is a person's name. I'm not sure about that one. So these are the newest elements. Newest as in they have been observed, and so now they have names, which gives us a pretty complete looking periodic table. These are now confirmed, so get rid of that. Pretty complete table. And so let's learn some about these. Now, there's a lot of cool information on this chart. We don't have time to go through all of that information on the chart or on the figure. So a vertical column is called a group. So we're going to learn about the halogens and the noble gases and the words are now totally missing my brain. Yes, alkali and alkali metals. We're going to learn about these. So those are the groups. And then a row is called a period. So we have groups instead of columns. and periods instead of rows. But you know what? We still call them rows and columns. So let's talk about these. Well, here, look, it's kind of color-coded. All of the periods are a different color. Let's make sure we understand this before I move on. The periodic table, as originally organized by Mendeleev, like I said, same chemical properties in one column, so each column is different chemical properties. And then more mass as you go down. That's the basic organization. Once quantum physics got involved, the quantum physicists realized that there is a special structure to this, and you notice that the first period had, how many elements are in the first period? 2. How many elements are in the next period?
10 or 9.
There's an additional 6. So there's 8.
What are you talking about?
I thought periods were.
So there's 2 in the first period, 8 in the second period. There's an increase in the number. The third period, in theory, you would have an additional 10, or an additional, wait, 10. No. 1, 2, 3, 4. I don't know why this is confusing me. Yeah, we could actually look at the numbers here instead of me trying to count. You added from 3 to 12, so yeah, an additional 10. So there's additional 10 in the fourth one. That additional 10, in theory, would come in the third period. But it turns out that energetically, it's lower energy to go down to the fourth first. So you're adding in theory, each additional period would have more elements. But because of the way energies work in quantum physics, it basically turns out that you go 2 periods and then you add in another set of elements. And so the table, if you had just the first period, you'd only have 2 columns. The second period, you have 8 columns. Third period, 8 columns. The fourth period, you have 18 columns. You go down more and you get to the 6th period, and instead of 18, you're going to add another, what is this, a dozen? 2, 4, 6, 8, 10, 12, no, 14. You add another 14. And there's just not much room to make a table that's adding 14 more. And so by convention, we show the 14 that physically belong in this gap here. They're only from these periods. We show them exploded out instead of in the table. So that's what those are. They are the elements that belong in the region there that I have just colored green. So if you follow the numbers, you'll see it goes cesium CS is 55 for the atomic number, barium 56, lanthanum 57, and then CE. Ooh. What's CE? I don't remember. Is 58. So that's the next one in the row. This 6th period subset is called the lanthanide series. Because it's the series that follows lanthanum. And then the one down here goes from actinide to thorium. So what do you suppose you call the series in the 7th period subset? If the 6th period subset is the lanthanide series, what would the 7th period be? Didn't follow the logic? Okay. After lanthanum comes this series here. Oops. Well, that one there. And so it's called the lanthanide series because it comes after lanthanum. So what would we call the next series? We have francium, radium, actinium. What would we call the next series? The what? That's right. It's called the actinide series. So those are the series that follow the name. So when you look at the chart, those ones down there in the bottom aren't hanging out by themselves. It's just taking space. So we don't have everything in. If you look at our table there, it actually has lanthanum is shown in the lanthanide series, and it takes the box where lanthanum is and it puts La through, and it probably says Lu, right? I can't read it from here because that's all those elements should be right there where that is. Okay, moving on. Sizes. What determines the size of an atom? What do you think determines the size of an atom? The what? Okay, you said the size of the nucleus, right? The size of the nucleus seems like a good answer. It's not the right answer, but it seems like a good answer because that's where you have the solid material. But I said Friday that atoms are mostly empty space. You have the nucleus, and the size of the nucleus is proportional to the atomic number raised to the 1/3 power, the cube root of the atomic number. So if you go from 1 to 100, the cube root of 100 is like 5-ish. It's a little under 5. So the size of the nucleus is about 5 times bigger at your largest element. If we went to 125, which we don't, we go to 118, you'd have a nucleus about 5 times bigger. The actual size of the atom is based on the electron cloud. Remember, the electrons are orbiting. We don't know how they're orbiting, but we can calculate where they're likely to be found. We can calculate the most likely distance from the nucleus to the electrons. And that's what we use to indicate the size of an atom, because the electrons repel other electrons, so we can only get atoms so close before those electrons start repelling really strongly. So these pictures here are indicating the size of the electron clouds. And you should notice 2 trends. In what direction does size increase? Going from where to where? I would have used the opposite. I would have said from right to left.
Yeah.
That actually seems counterintuitive because you have over here at rubidium, you have less electrons than over here at xenon. But the rubidium is bigger than the xenon. So that seems a little counterintuitive. More electrons, and it actually fits into a smaller region. What's the other trend? Up to down. So size is biggest at the bottom left-hand corner, smallest at the top right-hand corner. So you can get an idea about the size of the elements by where they sit on the periodic table. So that's the first thing that we can get from looking at the periodic table, some ideas about the relative size. Now here's the names for the groups. Now, yeah, they're called the groups. I was like, we call them, yes, groups. So the first one, alkaline metals. Second one, alkaline earth metals. This is hydrogen down. This is helium down. So hydrogen is alkaline metal, lithium is alkaline metal, sodium is alkaline metal, potassium is alkaline metal, rubidium, cesium, francium. Those are alkaline metals. What does it mean to be an alkaline metal? It means that you have, for the electrons in the atom, if you're on the right-hand side, I should have started there with the noble gases, the right-hand side. Those are called the noble gases because they're inert. They don't do anything. You can breathe helium. It's not going to cause you any harm, except for as it displaces oxygen. It just does nothing. Doesn't participate in chemical reactions. Why? Because Helium and all of the inert gases have what we call completed outer shells of electrons. The quantum physics that underlies chemistry says that you can fit a different number of electrons into each shell, well, period isn't the right term, but into each shell. And if you have all of your shells are completely filled, then the atom is just super happy. We've got positive charge, we've got negative charge, they're equal in size, we filled up all the shells. It's kind of like saying I have a box and I filled the box with everything that fits in it, I couldn't put any more in. It doesn't want any more, it doesn't want to give anything up because it's full. That's what we have for the noble gases. Well, if you go to the next, if you add one proton, that means you're going to add one electron for it to be neutral. But that electron is now hanging out by itself in a new shell. That's like saying, okay, so I filled this box completely, so now I have to start another box and I just have one electron in there. Well, that electron could go anywhere in that box, whereas the others are pretty much fixed in place. And that's what you have in hydrogen or the other alkali metals. You have one electron that's pretty much extra. So the atoms don't hold on to that extra electron very tightly. It's easy to give it up. And so that's why they all behave the same, because they have this extra electron that's easy to give up. Now, if you go to the next column, the alkaline earth metals, they have another special situation. In your lowest, your energy filling states, the lowest energy level can always have 2 electrons in it. And each period is starting a new level. So each time you get 2 electrons in the period, you have a little bit of stability because you have a little box that can only hold 2 that's filled. Even though in row 4, you're filling a total of 3 boxes. The first little box is filled when you have 2 electrons. So it's a little more stable because those 2 electrons are in their own little 2-electron box. There's still a lot of other empty spaces, but this is a little bit lower energy, so it's a little more stable. Then you go over to, notice no common names. Boron, carbon, nitrogen, oxygen, those are all in no common names. Well, I say no common names. The oxygen does have a semi-common name, so I did not learn this name until I taught the class. The halogens. But let's go to the halogens. From the noble gases, what's special about the noble gases? Noble gases, you have a bunch of spots for electrons, and each one has an electron in it. So the box is filled with electrons. Well, if you're looking at the halogens, whoops, that erased the wrong thing. If you're looking at the oh man, I am just really good at this. There we go. If you look at the halogens, you have one spot in the box remaining. Well, there's a lower energy if you can fill it. And so the halogens really want to get another electron to fill it. So if we compare the halogens with the alkali metals, the alkali metals have an extra electron they don't really care about. I mean, they care, but not a lot. It's like you're going somewhere with your little younger sibling. You're there with your friends, you got your younger sibling. Well, you care about your younger sibling, but you don't care a lot that they're with you. You could lose them at the fair and you wouldn't be so bad off. Whereas the halogens, they really want the additional. And so what happens if the two come together? Well, the alkali metal says, I got this electron I don't care about. The halogen says, I would love to have an electron. And so they say, hey, let's make a deal. Let's do a little getting together. And the alkali metal says, here, you go ahead and have my extra electron. Of course, that means I'm positive charge. The halogen says, yes, I got the extra electron. I'm complete now.
but now it has a negative charge. What happens if you have something that's positively charged and something that's negatively charged? They attract. And so they form a bond. First you had the transfer of the charge, and then you had this one's positive, this one's negative, and there's opposites attract. That forms a bond. We call that an ionic bond. It's an ionic bond because you made two ions. You had a neutral hydrogen with one electron. You had a neutral fluorine with a total of 7 electrons. The hydrogen says, have my electron, so now it's a positive ion. The fluorine has an extra electron now it's a negative ion, and then those two ions are attracted. So that's what an ionic bond is. So that's your most common type of ionic bond, is when you have something between an alkali metal and a halogen. So something that we eat all the stinking time, table salt. Table salt is sodium chloride. Sodium chloride. What's going on? You tell me. What's going on to make sodium chloride an atom? A molecule. Molecule is the name for multiple atoms being bound together. What's going on to make sodium chloride a molecule?
Sodium is giving up an electron. Making it positive, giving it to.
So the sodium says, I don't need this electron, and gives it up. And the chlorine says, I would love to have your electron, so it accepts it. So now we're going to have sodium when we put a plus sign to indicate that it has a positive charge now because it's missing an electron. And we put the chlorine with that's not an L. The chlorine with a negative sign to indicate that it now is an ion with a negative charge. And then opposites attract. So there's a force that pulls them together. What stops them from just crushing each other? Same thing that stops my wife and I from crushing each other. We can't share the same space. The electrons, when you get close enough, the electron cloud of the sodium is going to repel the electron cloud of the chlorine. And so they're being pulled together because they're ions, but those negative charges of the electron clouds don't let them come all the way together. Okay, so we've talked about the alkali metals and the halogens. The alkaline earth metals we've talked about, they have 2 electrons in that little box that's kind of a little more stable. But still they can give up some electrons. And the chalagens, the things in the category of oxygen, they would like to have 2 more electrons. Other things here, no common names. Semiconductors are kind of in this range. Those are semiconductors. So ones you may have heard of, silicon, obviously. More germanium than gallium. Probably better approximation like this for the semiconductors. But those are a special type of element. And then we have these here, transition metals. Why transition? Well, because they're between the alkali earth metals and the block that starts with boron. They're the additional group. So that's why they're transitioning here. Why metals? Well, because those are the things that we think of as metals. Even though we had alkali metals and alkali earth metals for the first 2 columns, most people don't think of sodium as a metal. Most people don't think of calcium as a metal. But everybody thinks of chromium, iron, gold, silver as metals. So those are the metals. Those are things that are good at conducting electricity as well as conducting heat, because they have electrons that are fairly free to move. Why are the electrons fairly free to move? Well, it must have something to do with the electrons going into this additional region that became available. And that's as far as we would ever get on that in this class. And we've already talked about the lanthanide and actinide series, so I'll leave that. Coming back to, no, I'm not going to install software in the middle of lecture, just for the record. Looking at our periodic table, I have highlighted here where lithium and fluorine are, and the question is, which is larger, a lithium atom or a fluorine atom? Okay, so we had 6, 2, 0. I'm glad that no one said there's no way to tell without memorizing the periodic table. Because what do we not have to do? We don't have to memorize the periodic table. But we want to see trends. And those trends for size, Danny, what were the two trends for size that we talked about? Okay, from right to left and top to down. So they're the largest here and the smallest here. And so based on what Danny said, we can see, well, these are on the same period. And so it must be that it's larger on the left side. So lithium was the correct answer. Identifying atoms using spectroscope. Now this thing's kind of cool. Back in the day, chemists didn't know that much about atoms, and they had a couple simple tests for the atoms. One test was by looking at the color. Another is looking at the surface features like smooth, rough, crystalline shapes. Another one was taste. Yes, you'd lick it. If you don't die, well, that's something that wasn't poisonous. They would also smell it. These days we don't like either of those taste or smell tests because you can damage yourself with both of those tests. And then there's the cool one. What happens when I stick it in a flame? Burn it, because by cool. You guys are probably way too young to recognize that quote. They burn it, they stick them in a flame. And different elements burn with different colors. And so they could identify by looking at the colors what the elements were. Now these days we have a much more sophisticated way. I should have brought it out now because we didn't cover the light. We can take a gas, and if we can, an atom, if we can get it in gas form, then we can send electrons flying by and we can make light come out. So when you look at a neon light, that's a gas that has electrons going through it, exciting it, and giving off specific colors that tell us about the energies of the electrons in the atom. And each type of atom has different energy levels. And so you have distinctly different colors. So for class on Wednesday, I'll actually bring out a lamp and we'll look and we'll see at the different colors we get from one type of atom. We'll only do one type. So that you can see that's another way that we can identify the atoms. And we call that the atomic spectrum. Since I'm going to show it to you in class on Wednesday, I'll just stop right here. Well, there's a pretty picture showing what happens when you burn it. Yay.